Okay, so we are going to have boosting algorithm today. It's a regression and classification both. It works. And boosting actually was developed keeping in mind that how you make how 1 minute. I'm just arranging my wires. They're too many wires around me. Okay, so boosting algorithm actually is a method of converting someone who's not a very good learner, a weak learner, into a strong learner. Okay, so you have in real life also you have some people who are very good learners and some are very not very good at learning. They are termed as weak learners, but I feel that somehow that in real life some people are blessed with photographic memory. They just read something and it just prints in their brain. Others take time, but then they can always learn. So based on that, this gradient boosting algorithm was developed, and the first algorithm which was developed was AdaBoost. Okay, so it was done long time back. So this theory actually it's on probability approximation, approximately correct. Sorry, PAC. We call it PAC, probability approximately correct learning. Okay, so it was way back in '88 when the paper came up on hypothesis of boosting problems, and that was long time back, 1988. So AI actually started long time back, but we just came to know about this recently. And there were other papers also in 2013, then so, so on. So there are many. You can have a look at the papers if you want to, but then that is not the name. So we have to understand that we have to understand actually boosting. So as it was based on that is I'll just paste some text there. So boosting, where is that? There you are. I'll paste it here. So for strong learner, how to make a strong learner, this idea was based on PAC, that is probability approximately correct, given by Leslie Williams' work on distribution free or PAC, what you call that. So this framework for investigating the complexity of machine learning problem, it was based on that. There is a paper also. I can share the link if you want to read it, but it's not required for now. Okay, but if someone wants to, then you can message me. I'll drop. Okay, so the first, as I said, was AdaBoost, and AdaBoost is like adaptive, you can say adaptive boosting or algorithm. So let me write here also the text. Right, here you are. This is the first. Okay, 1 minute. I did not do it properly. So AdaBoost was the first boosting algorithm, we can say, and it was like what he said, that adaptive boosting or AdaBoost in short. Right, now I'll just put some quotes here. Boosting refers to this their general problem of production, producing a very accurate prediction. Okay, so there will be rules combining rough and moderate inaccurate rules, and we call rules of thumb, that this has to happen. So there are certain rules of thumbs which have to be followed. So, and a boost, actually again, the aim is to make a weak learner into a strong learner, and it uses decision stumps. Okay, so it just splits the cells and uses something called decision stumps. And I don't know if you have gone read this graph theory or not. It's very common there in computers. We have graph theory, and if someone has done like in 12th C++, then they must have read that, or even in graduation when you're taught C, then in uh, data structures they tell you about this thing. So this decision trees and decision stumps you have, but for now I'll just put something there. I'll just put something so that you don't have to go back. Okay, so in Adaboost, the decision tree, it is the actually weak learner in Adaboost. They are the decision trees, and there is a single split. You would, when you are talking about boosting algorithms, just imagine a tree and how the branches are there, and you can invert it also and think of or something like an inverted tree and how the branches are there. So in case of Adaboost, there was only one split. There is only one branch, you can say, and called decision stumps for their shortness. Okay, and Adaboost works for weighting the observation, putting the more weights on difficult to classify instances. Suppose the uh, weights are basically the probabilities. Basically, you can say that what should be the probability of this event happening. So you can we used to decide the weights earlier, but these days we normally don't. And in the case of binaries, we used to have zeros and ones, and in between the weights we used to have. These days we don't have to do that. Algorithms are there and weights are already given, so you don't have to do that because they are already optimized algorithms. You can't do much about that. And when we say that optimized, that means they have been tested and checked for the best possible outputs, so they're already optimized. Okay, okay, then I can so we are not actually going into Adaboost. We'll be working on the cat boost algorithm. So after that, I'll just put something about cat boost. We'll be using cat boost. So it was just an introduction of Adaboost, that it is again an algorithm to make a weak learner strong learner, and that was it. Anyway, so we'll be working on cat boost. Now cat boost, it's a machine learning algorithm as we know, and uses gradient boosting or decision trees, you can say. Okay, and again, as all the models and the classifiers, this is again an open source uh, in open source library, or you can say that it is available as an open source library. So it is an open source, so anybody who wants to see the code can see. When we say open source, that means the source code is available for you. You can have a look at the source code. You want to modify, you want to change, you can do that. Okay, but this is gradient boosting actually is one of the most powerful technique for building predictive models. So if you want to predict something, then gradient boosting is one of the strongest, you can say, model. And a weak hypothesis or a weak learner is defined as you can define as a performance whose performance is not as expected, or as one thinks that it should be good, but it is uh, can be a little better. if you train it, or if you can, there is still a hope, you can say that. A person who can actually can be trained to perform better, something like that. Okay. So this has already given that. Some repetition, that's what I'll correct it later. There may be some repetition. Okay. So how you make a person more intelligent or a strong learner, you can say that. Not in more intelligent, everyone is intelligent, but a strong learner. Okay. How you do that? You keep repeating the things, you keep training the things, you keep practicing. Like if you are not very good at mathematics, what do? You keep practicing. You just take some examples, you take some examples, solved examples first, you solve them, see the technique, how it is working, you see the formulas, how the formulas are behaving, and then you have some unsolved problems, you solve them, you keep on practicing and you learn. Okay, so the idea is here is again to make a weak learner a strong learner, maybe by giving more training, or you can give more routines or more methods. Several times you have to repeat the methods. Okay, you do it, and then one day you'll find that the person or my code is working better. Okay, so you can put something about data boost. I've already done, but I'll put something here. Sorry, not the code. We'll come to the code and you'll see that it is so easy. So we have something more on data boost. I can put it. I'll just put all the query there first. I'll put query so that I don't have to go back and see. It is all how it works. So I'll just put it once for all. If there's some repetition, I'll remove that later. That's okay. Now that's okay. Let's go back and see that. Data boost I've already told you. Then we have generalized data boost and how we work on it and how the gradient boosting works on it. Okay. Okay. So we can, this is your generalization of data boost as a gradient boosting algorithm. So the framework, as I have already told you, that gradient boosting machine learning, it is basically you are just making a weak learner a strong learner by continuously training. That is what general you can say that, and we are putting the weights there. We are inputting the weights. We are increasing the weights and trying to train your network in such a way that it performs better. But there is when you're talking about a weak learner, that is a learner which actually can improve. Okay, so we have the gradient boosting, how it works. So when you have gradient boosting, there are three elements actually: loss function, weak learner, and then additive model. Okay, the loss function, again, how much losses are there, and you have to solve the problems. Function it use depends on the type of problems to be solved. uh, 1 minute, I have not moved it down. Okay. Okay, there are many standard loss functions which we use, and we have used earlier also in machine learning and deep learning also. We have seen the loss functions, and can use different functions to make to compensate for the losses. Okay, so regression uses a squad error, and classification may be using logarithm loss. So it depends. For a regression model, it could be any something like squad error. For a classification, it could be logarithmic loss. So it depends on what type of algorithm you're using. You can accordingly have your loss function. And manuals of all the algorithms have all the possible loss functions. You can have a look at that and decide. It is hit and trial. Basically, you put one loss function, see the output. If it is not working fine, you can change the loss function and see how it behaves. Okay, sometimes it is hit and trial, so there's nothing like very standard that for a particular data set this is going to work. But for benchmark data sets, we already know. Okay, because they have been tested and the algorithms have been tested already. Okay, so now when we are now the second thing is the weak learner. 1 minute, I just move it up. So decision tree are used as weak learner in gradient boosting. Okay, so regression trees, you can say specifically they are used at the output level, real values for splitting, and whose output can be added together. Okay, so this actually allows subsequent correct and the residual in the predictions. So that is subsequent model outputs. It helps in correcting the, you can say, the outputs or the predictions, decision trees. Okay, uh, so yeah, greedy algorithm, if you have seen, I'm not sure you have seen, but their trees are constructed using a greedy manner, in a greedy manner, that is choosing the best split point. Greedy is your you want to get the best. Okay, so it is choosing the best split points based on purity score. Like Gini, there is something like Gini score, or to minimize a loss. That is, the aim is to minimize the loss. So how they are split. So split. I told you, just imagine a tree, inverted tree, and how the branches are there. Okay. Uh, in case of adder boost, you have a single split, but in other algorithms, you have 4 to 8 levels. That means in adder boost, you have only one branch, one is split. But in others, it can be 4 level or 8 levels. That means uh, one branch is one. You can say that the branch is split into two. But in case of other algorithms, there are levels. Like one is connected with the other, and the other is connected with the other. So one branch is split into two. Then again, these two are again divided into two. Something like that. The levels are going down. Okay. So what you can see, you have some graphs like this where you can have similar levels, 4 to 8 levels. That means binary split. You can say one splits into two, then the left and the right again splits into two, then again left of the left splits into two. These are the levels. How it goes down the levels. Okay. So the idea is actually there are no levels. There are, you can say that they are the splits. You can call them layers also. These are the leaf nodes. Uh, that is one. One is the mother node, and then we have the branches where we have the leaf nodes. Okay. So maximum number of layers or nodes or splits or leaf nodes, you can say that. So a weak learner contains the weak specific ways. Okay. It is common to constrain the weak learner in specific ways. Like I can have the maximum number of layers. That means you can actually train, or you can make a weak learner a strong learner by having more layers or more learnings, you can say. In our case, more splits or more leaps or nodes. So what you learn from one at one level goes down, you learn at the next level also. So you keep on learning till you get the output. It is something like this. Okay. Then we have the additive model. Let me move it. Okay. Now trees actually are added one at a time. But the existing trees in the model are not changed. Whatever has been created, it doesn't change, but there can be addition of trees or the splits, you can say, or the branches, you can say. So, as I said earlier, also the idea of gradient descent procedure is to minimize the losses. All in all, what we have to do is minimize the loss and increase the accuracy. Okay, after calculating errors or loss, the weights are updated. That this is what we have to do. There are certain weights which are initialized with your branches or the splits or the trees, you can say. So these are the default weights. And when you train your network, the network finds that this is not sufficient. So it trains and it actually updates your weights so that you can have lesser losses and higher accuracy. Okay. So one way to produce a weighted combination of classifier with which optimizes is by gradient descent in function space. That is what I told you. The cost function we can costing also. We call the costing how much. When we say cost, it doesn't mean a monetary cost. We are talking about cost is how much weight or how much learning is required in our case. Okay, so you find the costing and you don't have to do actually the algorithm finds the costing and all and optimizes the weight so that you can have lesser losses and higher accuracy. Okay, so output when you're adding a new tree or when a new tree is added, the output of that tree is then added to the output of the existing sequences of the trees in an effort to correct or improve the final output of the model. Increases, right? So whatever output I've got from the new is added to the existing to improve the output. Okay, but number of trees are fixed for training stops once loss reaches an acceptable level. Uh, you may be thinking that my losses are particular should be 000 something like that, but when it gets the optimum results, when it finds that okay this loss is sufficient, okay this would be enough, the algorithm would stop. There would be no further branching. Okay, there will be no further splits. The moment it finds the optimum result, optimum accuracy or the minimum losses, it will stop. The algorithm will stop. Your things will work. Okay, so this is these are the three things we have. That is loss function, where we have to see the losses, what are the losses, and how we can decrease the losses, and then the weak learner, how to make a weak learner a strong learner by adding the weights and all. And then we have the additive model where the new trees are added and the output the new tree is added with the output of the previous trees, and the total output, the final output is updated. So it keeps on going, doing that till it finds that okay, this is an acceptable loss. And also it happens like sometimes we keep on doing that, we keep on repeating and keeps the suppose the model is learning, is working, and it finds a loss like 0.002 suppose, and it repeats for 4-5 iterations. Then it decides okay, this is the optimal loss, you cannot go beyond this, you cannot go down further, it cannot be 0.001, it is 0.002, and it finds that okay, in the last 5 iterations it was the same, so it will stop. It will say okay, this is enough, you cannot go further. But it can happen at some stage where it was 0.0 not 0.02 only. At that level also it may stop if it repeatedly gets the same loss output. Okay, so you will have to actually manage your data, and you have to manage your weights, or you have to manage the trees, the branching you have to give. When we give, when we train the network, we tell the branches, we can tell that also. So you'll have to manage your algorithms, and you have to see the data also, how you can improve the results. So it's not end of everything. The output, it can be different also. You can still improve it. So improvement on the basic gradient boosting, we have there are three things: tree constraints, and then weight updates, and stochastic gradient boosting. That is there. Sampling and subsampling is there. So we have seen already this tree constraints. That is, you have to see number of trees, number of leaves, and we have to see that there should be no overfitting. When there is overfitting, that is what all the machine learning and deep learning algorithms face. That is overfitting. That is, it jumps to the output sometimes because of overfitting. Okay, so overfitting is also not good. We have to avoid that also. So just have to see how it is done, and then we have the weights. As we have already seen that the weights are given, and if there are losses, then it tries to update the weights, and it can do is like when we added the tree, we have the additive model. From there also it can learn and update the weights. Okay, and see that we get a better result. So uh, now then we have the stochastic gradient boosting, which is again uses it greedy actually trees. It has to be greedily created. You can say that. Okay, samples and some subsamples are there from the training data sets, and it may be from the rows of the columns, create the subsamples, optimizes, and keeps on repeating till you get the correct output or the desired output. Uh, so aggressive model sampling would be like selecting 50% of the data, which it shows that it is more beneficial sometimes. So according to user feedback, using column subsampling prevents overfitting even more so than the traditional row subsampling. So we have row subsampling, column subsampling, and according to the users, like the person, people who have already implemented the algorithm, they have found that the column subsampling is beneficial, or it avoids overfitting. It's more beneficial, or you can say more productive than the row subsampling, which is actually the traditional way of sampling the data. Sampling is here just dividing your data into subsamples, samples and subsamples. Okay, that is how much data you're passing to your model at one time. Like we have the batch processing, something like that. Okay, then the fourth one, we have the penalized gradient boosting. Here the additional constraint can be imposed on the parameterized trees in addition to their structure. So classical decision tree, like we have the cart, cart. uh, these are the weak learner, so not used there. So classical decision trees like cart that we have talked about are not used as weak learners. They are not taken as weak learners. Instead, a modified form called a regression tree is used, that has numeric values in the leaf nodes. Okay, so we have the regression tree, also called the terminal nodes. We have the terminal nodes. We have the branching, the leaf nodes we have. So the value in the leaves of the tree can be called weights. So whatever the value is there in one leaf, like you, as I said, you imagine in an inverted tree, we have the branch. In branch, we have the leaf. So whatever the value is there in the leaf, that is taken as the weight. Okay. So the leaf weights values of the trees can be regularized using popular algorithms functions like L1, L2, regularization of weights. These are the different methods, L1 and L2. Okay, there may be additional methods to smooth the weights to avoid overfitting. So there can be many things which can be done. These are the theoretical parts we have with this, and then we have the CAD boost algorithm, that is machine learning again based open source library which used again on PSE, works similarly, and it is one of the most powerful these days, CAD boost, which is used, and we'll be seeing how we can do that. First of all, I'll have to install CAD boost. Theoretically you may not sorry, practically you can have a look at the things how they work, and they make more sense. But you can always look at the theory which is already shared. I've already put the theory there. First of all, we have to install CAD boost because it is not there by default in Colab, so we have to install it. Okay. All right. I'll just put the code here because I'm running out of time. I'll type it now. I won't complete this. Have a look and just run it and join you into this. Okay. So from CAD boost, import CAD boost regressor. Then we have this is the training set. We have just put a list with multi-dimensional array, and evaluation data is 4, 5, 6, 7, and the training data is 1, 4, 5, 6, 4, 5, 6, 7, 30, 40, 50, and 60. The labels we have to give -1, 0, and 1. This gives me the data from where I have to actually get. Then this is the model. CAD boost regressor we have called. Iterations 2, that means only 2 leaves, and those nodes you can say, and learning rate is 1 and depth is 2. Then you have to fit the model and then you have to predict. Okay, I'll just run it and join you into this. Okay. So we have run it, and you can see that this is just two levels. Iterations were two only, so there were two iterations here, and the output is 0. This is the predicted output. So model.predict evaluation data, that is evaluation data is 4567. 4567 falls in the, where it falls, it learns and it tells you 0. Okay, these are the labels actually, -1, 0, and 1. So 0 level, that is your second row, and that is the output you have got. Let me explain it again. You have some training data, which is a multi-dimensional array. Then we have an evaluation data, that is 4567, that is a single row. So you have to see the number of columns should be same when you are using a machine learning algorithm or a deep learning algorithm. So number of columns, they should be same. So because the number of columns are actually the features, so features should be same, rows can be different. Okay, so they are taken as the features. The columns are taken as the features. So features should be same, but rows could be different. Okay, number of data could be different, but the columns have to be same. Okay, now when we have the train labels, labels, I've given -101. It could be anything. It can be 1, 2, 3, 4 also. Okay, it can be A, B, C, D also, but it won't take the alphabets. Okay, so in this case, -1, 0, and 1. Now you have to create the model. In cat boost regressor, there are many parameters which we can give. Here I've used very simple parameters, iterations 2, learning rate as 1, and depth 2. That means two splits will be there, and the learning rate as 1 only. You can increase and see how much you want. But this is a very simple data. Then we fit the model. That is, we compile the model with the training data and the training labels. These are their labels and these are their data. Once it is ready, you put the evaluation data and try to predict the output. So model.predict, and you get the output. And that output is 0. So that means 0 is this row. It is matching with this row. Now, this is when we have the data which is there already and which matches your rows. But suppose you don't have a match. Okay, your data is, suppose it is not uh, the same. Like we have what we have 4, 5, 6, 7. Here also 4, 5, 6, 7, but it is not the case in this one. I'll put another one. Here it is 4, 5, 6, 7. It is 5, 6, 7, 8. This 4, 5, 6. This is the same thing, but what I've done, I've not done any changes here. I'll put another data here. 1 minute. 30, 40, 50. This is okay. Okay. The data is 1, 2, 3, 4. Earlier data was different. Okay. This was 1, 4, 5, 6, and 4, 5, 6, 7, and so on. Here it is 1, 2, 3, 4, 5, 6, 7, 8, and 30, 40, 50, and 60, something like this. This is in continuation. Now, if I train it again, it is going to give me 0 only. That means my second row matches with that. So that was like the data is already there, and the maximum match is there with the second row. So it gives me that. But if I change the data, the evaluation data, to something which is not there in my training and training set. Now training set has 1, 2, 3, 4, 5, 6, 7, 8, 30, 40, 50, 60. But my evaluation data now is 20, 21, 22, and 23. Training labels I have changed. That's not an issue. You can always have anything you want. I have made it 1, 2, 3. I can have 100, 200, 300 also, not an issue. Now iterations have increased to 4. Learning rate is 1, but depth I have increased to 8. Let's see. You can see that The iterations have increased to 4. Now what it gives me is 2.29, which is actually not there. This is 2. It is saying that it is not 2. It is 2.29. That is in between 2 and 3. Okay, so data, it is telling me that data is there, but it is not actually matching any of the data which is there in the training data set. So it is in between the second row and the third row, between 5 and 30. Okay, so it is 2.29. So close, if you draw a graph, you'll know that it is closer to that, to the values you have. There's a huge difference actually between 5 and 30. Let's increase the gap now. We'll have the gap and we'll increase the iterations. I'll not increase it right now. I'll just make it 10 and depth. Oh. You can see that. It is 200, 300, 400, 500, which is actually not there at all. It is telling me something close to the third row, but it is not there. So let me increase the iterations to 100 and see what happens. Let's see if the output we get 3 now, third row, but it is not in the third also, but we don't have more than 3. Even if I increase it to 90, so let's see what happens. There could be overfitting. It is again 3, so it is stuck at 3. Let me make it 200. There's no classes, there are no labels more than 3, so it won't get you more than 3. But what happens if I keep on training it? Nothing happens. Let me increase it to something very huge. Iterations have increased, depth I have not increased, because there is no need to do that. You can see that it has stuck to 3, so it won't go beyond 3. Right, so let me show you something if I can. Yeah, loss is, you can see, if there is a repetition it will stop, but since I have given the iterations, so it won't. So whatever you give, it won't make much difference. At 50, you can decrease the iterations, see where you get 2.99. You can have, let's say 90. I think 90 or 100 would give you 3 third class, but it is not actually in the third one, so it would be somewhere at 80 or something like that. You can experiment with the things, with the iterations, and see. And the depths also, learning rate also you can change between 0 and 1. Learning rate 1 means 100%. Okay. You can experiment with this data, and iterations you can actually change and see. And if you have similar data, this was not at all there. We have something which is related to row 3. 30 is there. Then we have 50, 55, and 56. Again, not there. Not all the values are there, but it shows that it's 2.99. If I increase it further, let's say I'll make it 80. It will give me this 3. Let's see if it is working at 770. You have to experiment actually with the values and see what is matching. It is 3. So I can reduce it further and see where the what could be the optimal iterations. Don't want to have more iterations. 60 is not working. Let's have between 60 and 70. It was there. So let's see if it was 70 or 65 would do. No, then 70 was working. So let's have 70. It matches with the third class, third row, sorry, third label. We get other outputs of every algorithm, whatever you are using, deep learning or machine learning. The output is a label only. Okay, So that is why labels are given, so that we can get the output and we can retrieve from the training data, the data you want to retrieve. You have done it earlier. So, a very simple example. You can have the data which is matching. If it is exactly matching, then you don't have to have the same number of iterations. You can always decrease that. Okay. Let's have something like this now. Training and evaluation, both are multidimensional. Training data and evaluation data, that is the labels you have for 5, 6, 7, 8, 10, 12, and 14. And the training data is 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 15, and 18. And labels are again -1, 0, and 1. So let's see. Columns are there. The rows are different. There are 2 rows now. Let's see what happens. It gives me 0, 0.437. That is 2. Outputs will be there. For the first one, 4, 5, 6, 7 evaluation data, the label here we have got is 0. That is, it is matching with the second row. Okay, it is matching with the second row. And the third, the second of this 8, 10, 12 is matching actually more than your between 0 and 1. You can say it is more than 0 and less than 1. 8 and 10, there are few values which are matching, like 12 is matching, 10 is between 9 and 12, and 14 is also there. So you can increase the number of iterations and see if you can get a better result. Sorry, 0.7, it is increasing, so let me increase it to 10 iterations. 0.9, so I can increase it further to 20, get it close to your third label. It is good enough, I think. If I increase it further, I may get a better result. Very close to. Yeah, this is very close to. So you don't have to do much. It's very close to this label one. That is the last row. 9, 12. Okay, so labels are matching and you get the output there. Okay. So it depends on, again, it's very simple cat boost, you can see. And you can have the strings here also. That is what is good about boosting algorithm. At boost, you can have the string data. And I have one example here. I'll just show you. I have something like this. Okay. Pool and cat boost classifier we have called. Training data is summer and winter. Summer 1924 44, 1932 37, 1980 37, summer 2012 204. These are the supposed number of students or anything in which year, how many students were there or something like that. Evaluation data, we have winter and summer, and the categorical features just 0. Training labels and evaluation labels we have given here. So there is a difference now. Training labels are there now and evaluation labels are there. France, USA, and UK. You can say this is for France, this is for USA, this is for USA, and this is for UK. And in this evaluation label, this is USA, France, USA, and UK. Now, train data set is pooling. We are calling pooling. It helps in actually uh, sequencing you can say the commands. Sorry, it pulls in the commands which I give, that you have to do this one by one. The things we have given, like we have given data is the training data, label is the table label, and cat features are the cat features. So just putting the variables in a uh, in a pool, okay, and then we can evaluate. This is the training data set. We have created the training data and the evaluation data set by pooling them together. Unknown caller. Okay. I'll just run it. I'll run it, and you can see this is the training into the trace is testing the same, and you can see the outputs as USA, USA, UK, USA. Okay, so let me show you what all outputs have got. That is the predicted class, probability, and the raw data. Three things we have predicted. So here evaluation is raw formula validation, prediction type is raw formula validation. We have other also, and here we have multiple classes. Iterations are 70. Learning rate is 1, depth is 2, and loss function here we have used as multi-class because there are more than one class. Okay, we can see that there are more classes here. Okay, so there are more than one class, so we have used multi-class model. We fit and predict, then predict the probability using predict probability evaluation data set, and then we get the raw formula validation using this function. So we have the class, predicted class, probability, and the raw probability. Raw formula we use for getting the raw validation. This is what USA, USA, UK, UK, UK and USA. You can match and see if it is matching with the data. There's no France. So data, we have 1996. So we don't have this. 1996, 68, 2000, and 248. So accordingly, it has eliminated France, which is not there at all. We have USA and UK only. 3 USA and 1 UK. Depends on the data actually. And depends on your labels. You can give any labels. So you can give string where labels also. Okay. I have to share it with you. We'll continue it on Friday. We have few more things to do with the cat boost. We can have and share it with you. I'll update this data sheet and you can practice on that. So this notebook I'll update. I'll put the rest of the examples also, but it's okay. They will. They're just very simple to work on, and then we can actually see it implemented on the real data set also. So we'll be doing that. So let's meet on Friday and see what all we have to do. Okay, we'll continue on Friday now. Okay, guys. So let me stop this recording and then